All right, today we're debugging a critical system error, not in silicon, but in the most complex piece of hardware we know of, the human brain. This is a story about a patch that fixes one major bug, but in doing so creates a cascade of failures somewhere else entirely. So, picture this. You're a sysadmin, you've got a critical error lighting up your dashboard. The solution? You push a massive system-wide update. You push it to every single machine in your server farm. It's a blunt instrument for sure, but it's a powerful patch for what looks like a total system failure. But what if that original bug was just a single faulty line of code on one specific server? The patch works, yeah, but the collateral damage from hitting the entire system, that could be catastrophic. And believe it or not, this is the fundamental challenge we're facing when treating Parkinson's disease. To really get what's going on, we've got to pop the hood and look at the system architecture. You see, the brain is running two primary dopamine circuits in parallel, and they each have a very, very different job. Okay, let's map these out. On one side, you have the circuit for action. This is your motor control loop, running through a region called the dorsal striatum. Let's call this the executor. It's the part of the system that handles physical commands. Then, on the other side, you've got the circuit for motivation. This one runs through the ventral striatum. We'll call this the evaluator, because it's all about processing reward, value, and deciding if something is worth doing in the first place. So there you have it, two distinct, parallel processing loops running on the exact same wetware. One loop handles the action, and the other handles the motivation for that action. They're definitely connected, but functionally, they are two separate systems. Now, in Parkinson's disease, the bug report that comes in is incredibly specific. This is not a software issue, we're talking about a hardware failure, and it's localized to just one of these two circuits. The logs are clear. The dopamine-producing nodes, the neurons, in a specific component called the substantia nigra start to fail. They just die off. This causes a critical signal loss. But, and this is key, it's almost exclusively in the dorsal striatum. The executor loop that controls movement gets corrupted. Meanwhile, the reward circuit, the evaluator, well, it's totally fine. It's still fully functional. So how do you patch a hardware failure like that? Well, we can't just replace the neurons. So medicine came up with this really ingenious, but kind of brute force software workaround. Let's call it the global dopamine flood. This patch is a molecule called levodopa, or L-Dopa for short. It's basically a precursor, a raw material that any neuron anywhere in the brain can grab and convert into dopamine. You're not fixing the broken part, you're just dumping raw material into the system for all the other parts to use. And this, right here, is the core design flaw of the entire patch. L-Dopa isn't a targeted function call. It doesn't deliver dopamine only to that depleted motor circuit. No, it acts like a global variable. It's accessible to and used by every single process that knows how to make dopamine, including that perfectly healthy reward circuit. And when you push a global variable like that system-wide, you get a massive conflict. We are literally about to fix one loop by dangerously overclocking the other one. The research papers really nail it. The unintended consequence, they say, is a dopamine overdose in the parts of the brain that didn't have a signal loss to begin with. You guessed it, the healthy reward circuit, the ventral striatum. So let's look at the data. Here's what's supposed to happen. In the motor loop, the signal is way down. It's degraded. After you apply the L-Dopa patch, look at that, the signal is restored to a normal functional level. The physical symptoms get better. On the surface, it looks like the patch worked perfectly. But here's the glitch. This is the other side of the story. In the reward loop, the baseline signal was already totally normal. But after we apply that same L-Dopa patch, that normal signal gets pushed way up into a dangerously high overclocked state. We've just flooded a perfectly balanced system with way more processing power than it was ever designed to handle. And the system errors that spin out of this are profound. We're not talking about a minor performance issue here. We're talking about a corruption of the user's core functions. You see things like impulse control disorders, compulsive gambling, shopping, or dopamine dysregulation syndrome, which is basically an addiction to the medication itself, hypersexuality, psychosis. The evaluator has been completely hijacked. So what's the big takeaway here? What is the ghost in this particular piece of code that we need to be looking at?
The L-Dopa paradox isn't just a list of medical side effects. No, it's a neuroengineering cautionary tale. It shows us that in our attempt to patch the physical machine, to fix the hardware that controls movement, we can accidentally corrupt the user's core programming, their decision-making, their motivation, their free will.
Which really leaves us with a fundamental and kind of scary question for the future of medicine and technology. As we get better and better at intervening in the brain's incredibly complex systems, how do we make sure that we're debugging the machine without corrupting the ghost within?